Hello and welcome to the second part of the Geometrical Optics Lecture for Optics for Energy. Today we are going to do a quick recap of where we left off last time. That's the matrix formulation for solving complex optical systems. And then we'll go on to analyze a few examples, such as the case for thin lenses and thick lenses, and then look at more examples for optical elements like mirrors and prisms. And I will also work out a few sample problems, and these will also be uploaded on the website, so you can take a look at them later on and try to solve them by yourselves. Okay, so let's begin with the case of a thin lens. So this is one of the most simple cases of optical elements, and by a thin lens we mean that if a ray of light enters from the left, goes towards the right, so if it enters the lens from the first spherical interface, it will suffer refraction and then immediately strike the right interface, suffer refraction, and come out of the lens. We are not going to consider a thickness for this lens, we are going to neglect that, so we won't write the matrix for the free space propagation for the translation through uniform medium inside the lens. Right, so I'm going to work that out. Okay, so over here I have the two matrices that we derived last time, the free space propagation matrix, or the translation through uniform medium, and the matrix for refraction at spherical surface. So let's quickly look at those again. So yeah, here they are. The translation through uniform medium and the refraction by spherical surface matrices. We are going to use these to solve all the problems that we are going to come across in today's lecture. Right, so let me solve the case for the thin lens. And I am going to quickly put down the problem over here. So this is my lens. And we are going to consider two different radii of curvature for the surface on the left and for the surface on the right. That's to give a very general idea of a lens. So let's say the surface on the left has a radius of curvature r, and that on the right has a radius of curvature r prime. Let's also assume that the lens has a refractive index of n prime, and everywhere else it's air, so n equals 1. So we are going to look at a case of a ray entering this lens from the left and exiting this lens from the right. Okay, so that's a summary of the problem we have over here. Like I said, we are going to neglect the thickness of the lens, so we are only going to consider the two cases of refraction at spherical interfaces. So I'm going to write down the matrix for this system like we did last time. The matrix will be n out because we have to look from output towards the input. So n out, alpha out, x out equals, the first matrix will be for refraction at the right spherical interface, so refraction, so let me name this interface as 2 and this one as 1. So refraction at 2. Then there will be refraction at 1. We are ignoring the thickness of the lens, so no translation through uniform medium. And then the input, so n in, alpha in, x in. Right? Okay. So let's look at the refraction at spherical surface. So remember, this is the power of the matrix formulation. You don't have to do the geometry and the trigonometry involved in solving these problems. You just have to remember the matrices and you can directly write them down. So we have 1, 0, and 1. For the more complicated term, we have n prime is the output, so in this case it's 1. The input refractive index is n, so that in this case the ray is going from the lens to outside, so refractive index of the lens, that's n prime, and the radius of curvature on that interface, that's r prime, and we have a minus in front of that. So let's write it similarly for the case of the first refraction. So in this case, the output is the lens. So the ray is going from the air to the lens. So the refractive index in this case is n prime minus 1 and r and minus. Hope this is clear. Also, the input was air, because the ray was traveling from air to glass, or from air to whatever the medium of the lens is, to be more general. So n in this case becomes 1, alpha in stays, so that's alpha in and x in. Also the output is again in air, so I'm going to write n out as 1, and we'll have alpha out and x out. Okay, let's do the matrix multiplication. So we have 1 times 1, that's 1, plus this term 1 minus n prime over r prime negative, times 0, that's 0. So 1 plus 0 equals 1. Next we have, we multiply so this times this. So 0, and so let's put down, so 0 multiplied by 1 and that term, so that is 0. Now we are left with the second term for the first row, so that is going to be 1 times minus n prime minus 1 over r, so that's, let me put down n prime minus 1 over r. There's a minus in front of this, and also there's a minus in front of the first term of the first of the second term of the first row of the first matrix. So I'm going to take the negative common and bring it outside the parenthesis. So let me just write down the term first. So it's this and negative in front of that. Hope that's clear. And lastly we have another 1, because we have 0 times the big term and then 1 times 1. So that 0 plus 1 is 1. Okay, and lastly we have this term. So that is how we write the matrix for this case. Let's tally with what we had in the slide, and let's see if we got that right. Okay, yeah, seems that that's the one. Right. So this is another example of how you use the matrix formulation to solve these kind of problems. The second term on the first row of the matrix is called the power of the thin lens. So why this is important, we will see in a couple of slides. Let's first define this term at least as the power of the thin lens. And if we do a little bit of algebraic manipulation on that, we get this kind of a term, which is n prime minus 1 times 1 over r minus 1 over r prime. So why this is important? So let's look at this term very carefully. The three variables that we have, n prime, that's the material of which the lens is made, and the 2 radii of curvature. So suppose you are given a situation where you know the input and you have to design a lens for a specific output. Suppose you have parallel rays or you're trying to do an imaging. So you know the input and someone gives you the problem to design a lens that will give you a specific output. So in this case, to build the lens, all you need to know is the material of the lens and geometrical parameters like the 2 radii of curvature. That's why this term is called the lens maker's formula, because this relates the output of the system to the input and gives you a matrix in which there is only one term with the 3 variables that are the material refractive index of the lens and the 2 radii of curvature. So that's called lens maker's formula. Okay, power of surfaces. So these are some general definitions of what powers are what powers of surfaces are. And so from the previous case we had already defined the term on the second term on the first row of the matrix as the power of a thin lens. So a lens is said to have positive power if it bends parallel rays inward. So this is when radius of curvature is positive. So these are the cases of the plano and the biconvex lenses. And a lens is said to have negative power if the rays bend outward. So that's when radius of curvature is negative on the left. From the matrix formulation, we defined the second term on the first column, so that's M12 as the power of the lens. So that's just summarized over here. And we know that the relationship between the power and the focal length it's an inverse relationship. So the focal length is 1 over power. Okay, so what happens when we have, instead of a thin lens, a thick lens? In the case of a thick lens, there's a finite distance inside the lens that the ray has to travel, which we neglected in the case of a thin lens. So remember, if you're going to solve this problem again, by matrix formulations, you have to write the output vector, the output matrix, as the product of a free space propagation matrix, refraction at spherical interface, translation through uniform medium within the lens, refraction at spherical interface, free space propagation matrix, times the input vector, times the input matrix. So more terms. But again, it all comes down to different versions of the free space propagation matrix and the refraction at spherical interface matrix. So all we need to do is keep those two matrices in mind, and we should be able to solve all of the, if not all, most of the problems that come our way in terms of analyzing complex optical systems. Right. So in the case of a thick lens, we can define two more planes other than the first and the second focal plane. These two planes are called the first principal plane and the second principal plane. So the first principal plane is defined as if a point source is placed at the first focal plane and a ray of light traveling out from it, the plane at which that ray of light hits and becomes parallel to the optical axis is called the first principal plane. That's shown by this ray over here, from the first focal plane to the first principal plane, and then goes parallel. Of course, if you remember, if it's a parallel beam inside the lens, it's not going to suffer refraction when it comes out of the lens, and it's going to go parallel to the optical axis. The reverse is the definition of the second principal plane. That is, if you have parallel rays parallel to the optical axis traveling through the lens, the plane at which they bend inward and come to a focus on the second focal plane, that plane is called the second principal plane. So these are definitions, but let's look at why they are important. So if you have a thick lens, it's not very easy to define what the focal length of the lens is. You essentially have a front focal length that's shown here, which is the distance from the first focal plane to the interface of the lens and the surrounding medium. But then the ray has to travel more distance before it comes to the first principal plane. So if we add these two distances, we get the effective focal length of the lens. Similarly, we can get an effective focal length behind the lens, and that's the sum of the back focal plane plus the distance between the interface and the second principal plane. So that's defined over here. These are again cases for the thick lenses, and thick lenses are what you would usually come across in day-to-day basis. So this is an explanation of what the significance of principal planes are. So imagine when we went from the thin lens to the thick lens system, the situation got a bit more complicated. Similarly, if we go forward and put in, say, more lenses, like say what you would have in a DSLR camera, or say the iPhone. So there isn't just one lens. Even the iPhone, even the phone cameras, they have at least 5 to 6 lenses, all packed into a very, very small area. And DSLR cameras have more complicated imaging systems, and they have very, very thin, thick lenses arranged in a particular order, and that's actually what you see in the big cylindrical lens that you buy. If you have a complex optical system, it's very useful to define the principal planes as whatever. So if we have the second principal plane inside a complex optical system, and if you have a parallel beam going into the system, it will eventually come into focus outside the optical system. And the plane at which it last encounters before it bends inward to the focus, that is called the second principal plane. So if you know the second principal plane, you can still analyze the system without knowing all the complexity involved. And that is also the same for the first principal plane. So that's what more or less the significance of these planes are. Let's look at the thick lens matrix transformation. What we had in the case of the thin lens is there. It's exactly the same, but we have put in between the two matrices one matrix for translation through uniform medium inside the lens. So the thickness of the lens is considered to be D1, and we have the two radii of curvature, and we have written the same equation as that we had for the thin lens, but we have put in the term in the middle to account for the ray going through the thickness of the lens. So we have, if we have a ray of light coming from the left, for the moment let's just consider the case when it strikes the lens and gets out of the lens. So it first undergoes refraction at this interface, then it has to travel this distance, and then refraction. So writing the output, we have output equals refraction, distance, refraction, times input. Same as the case of the thin lens, but you have one more term. But again, you can see that there's no more foreign terms than what we already had derived. The translation through uniform medium matrix and the refraction of spherical interface matrix. You just take those two matrices, change the values of the terms of refractive index and radius of curvature based on what is given in the problem, write the matrices, do the matrix multiplication, and that's it. You'll be able to solve the problem. So over here we go ahead and do the matrix multiplication. I'm not going to work this out. You can you can work this out by yourself, and you can practice a matrix multiplication and see if you get this term. It's a pretty huge term, but it's still straightforward. This is still a case of, this is a general case, and a particular case of this would be thin lens, when you can neglect the term in the middle. Okay, so this will give us the mathematical definition of what the effective focal length is. So if you remember what we defined previously, the power of the lens is negative of the second element in the first row. So the effective focal length, also the focal length is 1 over power. So let's look at that. It's 1 over power. So if we look at the second term, that is this one, we take the negative of that and do an inverse. We are supposed to get focal length of the system. But remember, the focal length of the system is the effective focal length if you have a thick lens. So you see the effective focal length f, and 1 over f is the power, which is nothing but the negative of this term. So those two terms are same. Okay, so this is basically wrapping up the different scenarios, like we are just going back and forth between different definitions, and this is essentially to show you that the matrix formulation is such a powerful tool, and if you keep that in mind and put in the matrices at the appropriate locations of your problem, you can bring down any complex system to an ordered an ordered multiplication of a bunch of matrices and solve it very easily. You don't have to do all the geometry and all that stuff. Right. So before we go forward with the imaging conditions, I have one sample problem to talk about. Let's see. Okay, that's here. So let's look at this. So this will be uploaded in the sample problems PDF if you want to look at it later on. So what this is saying is the case for refraction through spherical surface is shown below with its relevant equations. The equations describe a general situation where the plane is circular in nature. Hence the normal is defined as the normal through the tangent to the circular plane, which is the radius of the circular surface. That's over here. So you have a circular surface, and the normal has to be normal to the tangent to the surface, which essentially becomes the radius of curvature. Is it possible to alter this surface in any way to arrive at Snell's law of refraction in the paraxial approximation? The matrix formulation for the case is given below. So this is the matrix formulation. So output matrix, the output is inside the spherical surface, so that's n prime alpha prime and x prime equals the matrix times input case, that's n and alpha and x. And the matrix itself is again the case for refraction at spherical interface. So 1, 0, 1, and that complicated the second term on the first row. The case for Snell's law is shown over here. So is it possible to do any kind of manipulation to the problem and the matrix to go from the case above to the case below and essentially simply write what Snell's law would be? So why don't we think about this for a moment? Okay, I'm going to quickly solve this. If you already have the solution, you can tally with what I'm going to do. I'm going to write so this is sample problem 1. I'm going to quickly write the matrix for the circular for the refraction at the circular interface, at spherical surface. Sorry. So that was n prime alpha prime x prime equals. So this was the system description. Okay, so here R is radius of curvature, and we have to go from a case where we have a spherical surface to a case where we have a plane. So how do we do that? Let's just look at the problem for a while. So over here, the hint is that that R is the radius of curvature, and you're going from a spherical surface to a plane. So what is the radius of curvature of a plane? It's infinite. So a plane is defined to have an infinite radius of curvature. So if this was R, for the plane R goes to infinity. So now if we put R goes to infinity or in this equation, we have equals 0. So it becomes sorry, this is x. I don't know why I put 1. Right? And we do the matrix multiplication, and what we get is n prime alpha prime equals n alpha, and x prime equals x. So remember, if you remember, this is Snell's law in the coaxial approximation. So Snell's law is n prime sine alpha prime equals n sine alpha, and in the coaxial approximation, sine of theta equals theta. So that's that. So that will give you an intuition into the what the physics is going on, apart from just the math. So we put the radius of curvature as infinity, and that essentially gave us the Snell's law. That's why we took up the case of the spherical interface in the first place, because it's a very, very generalized situation, whereas a plane is a more particular situation for the spherical surface refraction, where the spherical surface has infinite radius of curvature. Okay, so let's get back to the lecture. By the way, you'll find the sample problem in the sample problem PDF, and it has the solution, so if you want to look over that. Okay, imaging conditions for ray tracing. So far we have come across different optical systems, and we have used light rays to solve different situations relating to these optical systems. This is again, so what was the use of learning these matrix formulations? So in effect, if you're going to design optical systems nowadays, maybe for your project, for imaging, non-imaging cases, no, you're not actually going to solve these matrices by hand. So we have these softwares which can do all of the things that we did so far, and one of them is light tools. And I think you're going to have a lecture on light tools, and you can use that to simulate your projects, whatever it is that you're going to make. And it's a very, very powerful software. It's a very, very powerful ray tracing software, and it gives very good results. But essentially, when those softwares are written, these kind of matrices are used inside those softwares to solve more complex scenarios. And if you're going to plug these into a computer and use the computer to solve these matrices, it's going to make your life a lot easier. But it's worthwhile learning how those programs are written in the first place, and that's how these matrix formulations come into play in day-to-day lives when you're actually simulating or designing optical systems. And those softwares work again by the same principle of ray tracing. And this brings us now to a case of imaging. So far we were talking of optical systems in a very generalized case. Now let's assume an optical system which is specifically used for imaging certain objects. So let's say a telescope or a microscope and so on, or a DSLR camera lens. So in that case, we have this object on the optical axis with a finite height, from which different rays emanate, and they go through an optical system. It's not drawn over here because we can consider any optical system, and all the rays come back to a point and recreate something similar to the object, which is called the image. So the image point is located at the common intersection of all rays emanating from the corresponding object point. That's already drawn above. And rays passing through the two focal points. So let's see, the third ray over here from the top which passes through the first focus, and the first ray over here, which passes through the second focus, are the chief rays that can be directly ray traced through the system. Now let's look at what we mean by imaging condition. So if we write the system matrix for this case, again you're looking from the output toward the input, you will write output matrix, output vector, as multiplication of a matrix for free space propagation of distance s prime, then a matrix for the optical system, and then free space propagation for S. So we have written that over here, and because this is a very general case, we have different refractive indices, n prime and n. So the free space propagation matrix, or the translation to uniform matrix, uniform medium matrix, was 1, 0, d0, 1 over n. So d0, 1 here becomes s prime for the first case over n prime, 1. And then for this optical system in general, so if we go back to what we derived, say here, let's see where it goes. Yes, over here, so we had 1 as the first term, then 0 as the first term in the second row, and 1, and then we had this big element that we called the power. So there's no need to write all that, because this will change based on what the optical system is. It can be a thick lens, a thin lens, and so on. So this term generally changes, but we can call this as the power, so P. So that's what is written over here. Let's see. So yeah, so it's 1 minus P, 0 and 1. And then again a matrix for the translation through uniform medium for the first case. So you multiply that and you get the big final system matrix. So now, what is the imaging condition? The imaging condition means that when you have a proper image, all the rays that came out of the object must have been collected by the optical system and brought in to one point, which is the image. So the rays must come together irrespective of what the angle at which they came out from the object. So this term over here has to be independent of the angle. So and also because it gives you position, it has to be independent of alpha. So x prime is independent of alpha. So this term, if the imaging condition is satisfied, cannot exist. That is, it must go to 0. How do we use these in problems? I will come to the second sample problem, but let us see where this problem leads us to. So if we set this term to 0, it gives us the imaging condition n over s plus n prime over s prime equals p. Also p, you know, is 1 over f. And if we consider a case where everything is air, we can replace the n and n prime by 1. So if you remember your high school physics, the 1 over s plus 1 over s prime is actually your 1 over object distance plus 1 over image distance equals 1 over s, 1 over f. That's the formula for the lens imaging condition that we had learned in high school. And this gives you a more powerful approach to the simple formula. So when we learned that, we had this case of imaging, and we had object distance, image distance, and focal length. And we had a law or a rule to relate those three. So now, in this lecture, we derived different geometry and matrices and essentially came back to that same formula. But we now know general situations. So if we have simple systems, we can use this formula. If we have complex systems, we can go back to our general matrices and solve them. But again, it's all tied back together. And again, we learned something called magnification. And the magnification, if you remember, is defined as the height of the image as the ratio of the height of the image to the height of the object, so x prime over x. Put it from this equation and you would get 1 minus p times s prime over n prime. You can work this out if you want. Alpha and alpha prime. So this is for angular magnification. This is the angle at which the rays are emanated and the angle at which the rays are collected give you something called angular magnification. So that's delta alpha prime over alpha prime, which is defined over here. Okay, so this is the generalized imaging conditions, and this is kind of like a recap slide that shows you the image is the output in any imaging conditions. So the output matrix is the image matrix equals the system matrix times the object matrix, which is the input matrix for imaging systems. The power P equals the negative of the second element in the first row of the system matrix. The imaging condition is the first element of the second row goes to 0. Lateral magnification is the second element of the second row, and angular magnification is n over n prime times the first element of the first row. So this is a very, very important slide which summarizes all the different conditions for imaging and all the different mathematical formula that is related to them. So now, before we go forward for aperture stops and field stops, so this is the sample problem that we are going to work out. So there's two parts to this problem. I'm going to work out the first part. The second part is identical, and I encourage you to work that out by yourself and tally with the solutions. So this problem and the solutions are going to be in the sample problems PDF, and that should be uploaded on the website. This is an imaging problem, and we are going to make use of the imaging conditions and the set of imaging matrices that we derived just a while back. So let's look at the problem. It says that there's this fish that is located at the center of, the sphere of refractive index n. The location of the fish from the interface separating the inside and outside of the sphere is S prime, which also happens to be the radius of curvature because the fish is located at the center. So S prime equals R. And there's this person who's looking at the fish, and he's located outside the sphere at a distance of S. So the first part asks us where the image of the fish is formed, what is the magnification, and if the image is real or virtual. So first off, I did not talk about the cases for the real and virtual images, but I'm going to discuss them as I work out this problem. So let's actually work this out, and I'll talk you through the imaging conditions. I've drawn a simple version of the problem over here with the fish and the observer. Okay, so like we just discussed, and what we remember from the previous matrix formulation cases, we're going to write the output matrix in terms of the multiplication of a system matrix and an input matrix. And in the case of an imaging condition, the output matrix is nothing but the image matrix, and the input matrix is the object matrix. So let me write the image matrix as Ni alpha I. I stands here for image, not to be confused with input, and the object matrix as No alpha O XO. Again, O stands for object. So let's look at the direction of travel of the light. So in this case, light travels from the fish to the observer. So light travels from right to left. So remember, this is the first case. So remember, we have to apply the sign convention and consider certain distances as negative. So if our output is the observer and the input is where the fish is, the light is going to first travel the distance S prime inside the sphere. then it's going to suffer refraction at the interface. So I'm going to put those down. So first, the matrix that we're going to write will be for free space propagation inside the sphere. The second matrix will be for refraction at this interface, and the third matrix will be for, again, free space propagation to the observer. So to the observer. So for the first free space propagation matrix, we are going to look at what our free space propagation matrix was: 1, 0, d0, 1 over n, and 1. So d0, 1 over here is S prime. So let's write that. Oh wait, actually, no, so that's wrong, sorry. Yeah, so this is actually what we have to be careful of, and I almost made a mistake there. The output is the observer, and the input is the fish. So we have to write from output, we have to write the matrices from output toward the input. So our output matrix equals first the free space propagation in S. So d0, 1 in this case is going to be S, so we'll write 1, 0, S, which essentially S over n, and n is equal to 1 in this case. So S over n is 1, and then 1. Then we'll write the matrix for refraction, and for refraction let's look at the matrix. So it has 1 here, 0 here, and 1, and then minus n prime is the refractive index on the outside, which in this case is 1. So 1, n is the refractive index on the inner side. So in this case the light is coming from inside the sphere, so that's n, and r will become minus r because light is traveling from left to right. From right to left. Let's write the third matrix. That's easy. 1, 0, S prime over n, and 1. So now, in this case, so we can put in a few things. So Ni equals 1 because this is air. On the image side is air. No equals n, that's inside the sphere. S prime equals r. So we have n, so n becomes 1. So alpha I x I equals 1, 0, S1, 1, n minus, the negative signs above and below cancel out, so we have 1 minus n over r, 0, 1, and we can write 1, 0, r over n and 1 times n alpha naught x naught. So this is your system matrix. Okay? Alright, so you can do the matrix multiplication. I already worked that out, so I'm going to write directly what the result would be. That would be 1 minus n, 1 over n, then 1 minus n over r over n plus s over n, and over here we'll have the last term will be 1 plus s times 1 minus n over r times n alpha naught x naught. Okay, so firstly we have to, so let's look at the questions again. We have written the matrices. The question is, where is Vander's image formed? So first we have to answer what is the imaging condition. So since the question asks where the image is formed, we know the imaging condition is satisfied. So in order to satisfy the imaging condition, what we just learned is that the term m21 has to go to 0, which here is r over n plus s over n equals 0, and this implies s equals minus r. So r was the radius of the sphere, and that essentially means that the image is at the center of the sphere. What does the negative sign mean? So the negative sign means that the image is virtual. So I'll explain what I mean by that. Since the light is coming from a refractive index which is higher on the inside from where the light is coming than where the light is traveling from, light rays would bend outward. So let's look at light ray traveling like this. When it hits the interface, it's going to bend outward. Similarly, a light ray, so I'll have more space, let me draw over here. A light ray coming out from this is going to bend outward. So they are not ever going to actually converge toward the observers, but toward the observer. But how are we going to see? So what the eye does is it actually traces the path of the light ray back to where it actually originated from, and we will actually see the image at the center of the sphere, which is the center of the ball. But this will be a virtual image because the light rays did not actually converge at that point. It formed a virtual bundle of rays coming to a convergence at one point. Hence the image is called virtual, and mathematically this is shown by the negative sign in front of the image distance. Okay, so going forward, let us calculate what the lateral magnification would be. Sorry. So lateral magnification, we know, is image distance over object distance. So if you do the multiplication, you'll see that this is equal to 1 plus s over r. You do the multiplication and solve the equations. S over r times 1 over 1 minus n. And we already know that s equals minus r. So this is equal to, so magnification lateral is equal to 1 minus 1 plus n. So this is equal to n. Alright, so that is your solutions. That solves the problem. So this is one solution and this is one solution. You can go over the other part of the problem by yourself, and you'll also find this solved in the sample problem document. So I urge you to solve it by yourself and then once look at the solution and make sure you got that right. Okay, let's go back to the slides and go forward. Right. So now we come to aperture stops and field stops. So the aperture stop and field stop are actually two apertures, both which are used to contain the amount of light. The aperture stop is an aperture which is placed very close to the lens, and it controls the amount of light reaching each point of the image. So let's look at this over here. Let's say the green beams or the green rays of light emanate from the bottom of the object. They go through the lens and they come to a convergence at the image, again the bottom point of the image. Now if we place an aperture and close it down, we are going to limit the number of rays or the number of angles at which the different rays are accepted by the lens. Imagine the aperture was wide apart, you would collect all the light from the different points of the lens. As you narrow the aperture down, as you close it down, you're going to limit the amount of light which is reaching the image, and that is the definition of the aperture stop. For the field stop, imagine the aperture stop isn't there and all of the light rays are coming to the image. If you place an aperture which is very close to the image point and close that down, then you're going to limit the number of image points that are going to be formed. Essentially, you're going to block different rays of lights that are going to form the image. Why this is important is because the aperture stop lets you control the amount of light that is going to form the image. So imagine if you are doing photography and you have a very, very bright source of light, you can close down your aperture and control the amount of light reaching your sensor. So one thing to remember is that since the aperture controls the light, that is going to be placed close to the lens. And since the field stop controls the number of light rays reaching the image, it's going to be placed closer to the image, or in case of the camera, the sensor. Okay, so entrance pupil. So entrance pupil is defined as the image of the aperture stop as seen from the object side. So if you're looking through the lens from the object side, what happens is all the light rays that are being blocked by the two ends of the aperture stop, your eye will trace out the light rays and give you a virtual image of the aperture stop. This is called the entrance pupil. The reverse case gives you the exit pupil, where you see the image of the aperture stop as seen from the image side. Okay, so now we will look at some more optical elements. We have completed the first part, which consisted of different kinds of lenses. And now we are going to look, so the lenses function from refraction. And now we are going to look at some optical systems which function from reflection. And in this case we have mirrors, and we will have another optical system called the prism. It also functions from refraction, and it gives us a new optical phenomenon called dispersion. So let's look at these. These slides are recaps of what we already discussed. So lenses, let's remember that lenses are the main instruments for image formation. They collect light emanated from a point source and make the light rays, which were initially divergent, converge at another point on the optical axis, which is defined as the image point. We talked about the cardinal planes and points, like the first focal point, the second focal point, and the two principal surfaces. And we went through matrix formulations and discussed imaging conditions and magnifications. Okay, so now we come to prisms. Prisms work also by the phenomenon of refraction, and so here's so essentially they are refracting optical systems. So if we assume a symmetric case, and by symmetric case it means that a light ray which is coming in at an angle A will exit the prism at an angle B, and these two angles are equal. We will get that if we draw the normal to the plane on the left hand side, the angle that the ray makes to this normal, A prime, equals the angle the ray makes to the normal on the other side, which is B prime. So if you look at this, the dotted line on the left hand side, that's the plane, that's the normal to the plane. So A is the angle of incidence and A prime is the angle of refraction. And on the other side, B prime actually is the angle of incidence, because now the ray is traveling from inside the prism to the outside, and the angle B is the angle of refraction. So we can do a little bit of geometry, and we can write two relationships of A prime and A with respect to the prism angle theta and this angle D, which is the angle, the alternate angle of the two beams, of the two rays of light when we traced back. So this is the ray of light traced back, and the incident ray traced back. That's the alternate angle. Okay, so from Snell's law, so Snell's law would give us on the left hand side 1 times A, because the outside refractive index is 1, equals, so this is paraxial approximation, or you can also consider sine theta. So for paraxial approximation you would have 1 times A. For the actual case, when the paraxial approximation isn't valid, you have 1 times sine A. And on the inside it equals n times sine A prime. So now if you solve from that equation and replace A and A prime, so it becomes n equals sine A over sine A prime, and you have a relationship between the refractive index of the prism, the angle of the prism, and the angle between the two rays. So don't worry too much about the math, but let's try to understand what is going on using the physics. Suppose you're given a case where you have to design a prism, and you know the refractive index of the material out of which the prism is going to be made. You know the angle of the prism, or if you don't know the angle of the prism, you know the angle at which the rays are going to come. You can basically equate these three parameters in one equation, and that is given over here. So if you know two of them, you can calculate one. This is similar to the case where you have the lens maker's formula, and you could design and construct lenses based on outputs desired for specific input situations. Okay, so the next property of the lens is the property of dispersion. Dispersion means that if you have white light, which is composed of all visible wavelengths, coming in from one side of the prism is going to refract that white light, and the refraction suffered by different wavelengths is actually different. So when the light rays come out on the other side, the white light is going to be split up into all the different colors that compose it. This is called Newton's prism because Newton has a relationship with it. He is credited with being the first person to observe this phenomenon at work. Now, what is important is that Newton's genius lies in the fact that he did not stop there. What he actually did was he took one of these beams, suppose the red, and closed down all the other beams using an aperture. So he put an aperture that's like a black screen with a hole in the center, so that only the red would pass through the hole. So he placed another prism in the path of the red, and he saw that that ray goes through without splitting into any other constituent colors. And that means that these different colors cannot be split into any further colors. So he was able to conclude that these are the colors that make up white light, and they themselves, individually, they are distinct colors that themselves are not made up of any other colors. Obviously, we know nowadays that within white light there's literally hundreds and thousands of colors, but essentially our eye cannot make much of a difference, and it's said that we can detect up to like 30 colors. Like you can differentiate between a darker shade of red, lighter shade of red, pink, maroon, and maybe where the red comes from orange, and different shades of green, and you can detect all like a few different colors, more than 7 of course. And if you have more sophisticated technology, if you have more sophisticated machinery like spectrometers, you can map out all the different wavelengths, and the finer your instrument, the finer you can split these light rays. And each of the wavelengths have different, and each of the colors have different wavelengths. So imagine red is around 600 nanometers, green is around 500, blue is around 400. But if you go from blue to green, you can go from say 400 nanometers to 401 nanometer, 2 nanometer, and so on. So you would have literally hundreds of different colors, each for a different wavelength. And you can make those distinctions in spectrometers, but still all spectrometers essentially work on the same principle as Newton's prism did. Okay, so this is some math related to the measurement of dispersion property of a prism. First, we define 3 primary color lines, or 3 reference color lines, one for the red around 600 nanometers, one for the yellow around 500 nanometers, and for the blue around 400. Now we look at the refractive indices that crown glass has, and why crown glass is because it's one of the most common and traditionally or historically important glass types or materials out of which prisms were constructed. And we define the refractive index of crown glass with respect to these 3 wavelengths. So a refractive index value for the F, D, and the C lines. and you have different refractive indices. One thing to notice is that as the wavelength increases, say from 400 nanometers at the F line to 600 nanometers at the red line, there is a very, very small difference in the refractive index, but it essentially decreases from, say, 1.53 to 1.52. It's minute, but it's important to notice the difference, which tells you that the longer the wavelength, the less the refractive index becomes, which means that the red light suffers less refraction than the blue light, which is something you can look at here. So the blue light bends closer in towards the prism, while the red light bends much less compared to the blue. That is because the refractive index offered to the red light is lower than the refractive index which is offered to the blue light. Okay, the definition of dispersive power of a prism is NF minus NC over MD minus 1, and the dispersive index is the inverse of the dispersive power. So these are different parameters that you would require if you're designing and constructing prisms for specific applications. Next, we come to an optical system which works using reflection. So previously lenses, prisms, they all work using the phenomenon of refraction. And mirrors are the ones which work on the law of reflection. So very simply, and we know this already from high school, that if we have a point object, P, and a light ray goes up from P, it strikes the mirror and is reflected back. The angle of incidence and angle of reflection are same. If you now look at point P prime, your eye will trace out a ray back through the mirror to a point which is located at the same distance away that P was away from the mirror. This point is called P double prime, and this is the image formed by the mirror. So the image formed by the mirror is actually virtual image, always virtual image, and the fact that this geometry is valid, the image will always be formed, and it will look like it's always being formed at the same distance away from the mirror as the object is. Now, of course, this space doesn't exist, and it's an illusion of depth which is created by our eyes. But this is the phenomenon which gives the idea of depth or a space behind the mirror. Essentially, the mirror is just a flat plane, and it's an illusion which is created by our eyes tracing out the path of the light. So plane mirrors have zero power. This is pretty obvious because the light rays are always going to be traced back equidistant. So the image size will always be equal to the object size. And this is only true for plane mirrors, however, because there's no focusing or imaging going on apart from simple reflection of light rays. The image is always virtual. This is something we already discussed. And they're laterally inverted, so left becomes right. Okay, so now we come to sign conventions for reflection. It is kind of the same that you had for the case of refraction and lenses and so on. That is, the convention is that light travels from left to right before reflection and from right to left after reflection. And the radius of curvature is positive if the surface is convex towards the left. Longitudinal distances before reflection are positive if pointing toward the right, and if they're pointing toward the left, they are negative, and it's true for reflection. Okay, longitudinal distances are positive if pointing up. So this is something that you have to keep in mind when you are solving problems related to mirrors, like we did for the case of lenses. And you remember in the sample problem we showed that since the light from the fish was going toward the observer, was traveling from right to left, we considered the radius of curvature as negative. So these are, again, you have to keep them in mind when you're solving problems. Okay, so this is a case of imaging with mirrors, and the first example that we have is that of the spherical mirror. In the case of the spherical mirror, we are again going to consider the paraxial approximation, and that is that the light rays are traveling very close to the optical axis, and they are parallel to the optical axis. So what happens is that in this situation, when you have a spherical surface, all parallel beams, when they hit the spherical surface, they will be focused to a common point which is located at somewhere on the optical axis. So let's take a look at exactly what is going on over here. Suppose, let me draw the case. So I have this big sphere, suppose, and I'm just going to look at this portion, and I have the optical axis like so. And so let's put down the different tangents. So suppose we have a tangent over here, and we have a tangent over here. The tangent over here is obviously going to be perpendicular to the optical axis, then one over here, and one over here, and so on. And if those are the tangents, the normal to the tangents would be like, sorry, let me draw that. The normal to the tangents would be, say, like this, and like this. This one is obviously on the optical axis, then this, and this. And what happens is, if you have parallel beams coming in, of course, you can see that the beam which will be traveling along the optical axis will simply be incident normally, so it would be reflected back. The one that would be traveling, say, like this, would then be reflected at the same angle as it was incident on the mirror. Then one which is like this goes like that, and the one which is coming in like this, sorry, so you could draw that. So the beam which is the beam which came in like this is again going to go like that, and the beam which was again parallel over here is going to go like that. So what happens is, all the beams are going to be focused down to a spot over here. So this is a region where all the beams will be collectively focused, and that is what is shown over here. So the question is, could we improve this scenario and go from this blob of light to a perfect focus point where all the beams come in and are focused sharply to a point? So this is the case of, say, the perfect focus. Can we achieve that? Or rather, I put the question in this manner: for the circular mirror, the function that describes the mirror surface is the circle. What function would give you a perfect focus? So why don't we think about this for just a while? Right, so the answer is, if you remember high school mathematics, the curve would be a parabola. So the function that describes the perfect focus is a parabola. That is because that is the definition of the focus of a parabola, is that, so if you have rays coming in, so this one will be reflected back, and say any parallel rays which are coming in are all going to be focused at exactly one point. And that's the beauty of the function of the parabola. So again, this goes here. And so on. So the definition of the parabola was that the locus of the point which maintains a fixed distance from another point, and a line which is called the directrix. So here and here. So this was your directrix. Right. Let's quickly look at that. So here is the definition of the parabola. So that is why you can achieve the most perfect focus while using reflection, not in the case of a spherical mirror, but actually in the case of a parabolic mirror. And that is what we are going to see over here. The paraboloid mirror is the case which offers you the perfect focusing. This is actually why all satellite dishes, radio antennas, radio dishes that you look at all appear to be in the form of a paraboloid mirror, because that offers you the best possible focusing. And the receiver of those satellite dishes and antennas is located at the focus of that parabola. That's why parallel rays, say for communication, or say if you're looking at X-rays or gamma ray bursts from different distant galaxies, they all come in as parallel beams. They will all be focused at one point, which is the focus of the parabola, and that's where you want to put your receiver. So we would have similar mathematical formula to describe the imaging conditions for reflective optics. And if you remember, the lens formula was 1 over image distance plus 1 over object distance equals 1 over the focal length. It's the same as in the case of the lens. It's the same here. So 1 over image distance plus 1 over object distance equals 1 over focal length. And the focal length is given by the r over 2, which is the radius of curvature divided by 2. Okay. Similarly, you would have angular and lateral magnifications, and that is given by the image distance over the height of the image over the height of the object, and the ratio of the image and object locations. Alright, so you can have magnification and demagnification in case of mirrors other than plane mirrors. So these are different cases which are not the same as in the case of plane mirror, where magnification doesn't take place and the mirror has no power. So power in the case of plane mirror is 0, which is 1 over f. Right? Okay, so now moving forward, what we discussed with the parabolic mirror was the tendency to approach perfect focus. Of course, in real life there is no perfect optical system, and that is because mostly it's very difficult to construct these absolutely perfect surfaces which are defined by mathematical functions. You would also not have you would also mostly not have perfect wavefronts, and why that happens is because light actually it doesn't travel through exact vacuum, and you have a bunch of stuff like molecules and dust particles that light, if it's radio waves, it's like buildings, because radio waves are much bigger, and if you have visible light, it's dust particles and so on, that will interact with the wavefront and create disturbances. So any deviation of the wavefront from its ideal spherical shape due to imperfect reflection and refraction by the optical elements, and also from the matter that it has to encounter on its path, is called aberrations. But mostly aberrations are defined in terms of being formed by imperfection in the optical system. So optical elements like lenses and mirrors are always prone to these imperfections, which hinder the ideal processing of light in most situations. So let's look at one of those aberrations. This is called chromatic aberration. This is because the index of refraction varies with wavelength. So this we already discussed when we were working on the case of the prism. The refractive index for blue is greater than the refractive index for red. So essentially red light suffers less refraction than blue light. So if you have white light coming into a lens from one side, the white light is not going to be properly focused at one point. The blue part of the white light will be broken out and it will come to a focus closer to the lens, and the red light part is going to focus further down the distance, down the line on the optical axis. So this distance is called the longitudinal chromatic aberration distance between the focus point of the blue and the red light. How do we correct these chromatic aberrations? So one way to do that is to compensate for the difference in the refractive index by joining two optical elements together. The first kind is called the crown, and this has more positive power. So firstly, it's a biconvex lens, sort of an optical element, and it is because it's biconvex, it has positive power. And the second is concave, so it has negative power. So the crown can have more positive power and has moderate dispersion, while the flint can have lower negative power and has high dispersion. So the total power of this system can be written as the sum of the powers of the two elements. Now, if you remember from the matrix formulation for the case of refraction at spherical interface, the second term in the first row was the definition of the power. So for each of these individual powers, and that's how we derived the lens maker's formula. So if you remember, we were able to equate we were able to make a relationship between the refractive index that makes up the lens and the two radii of curvature. So that's the same given over here. So imagine the crown and the flint have different refractive indices N1 and N2, and they have different radii of curvature. You can write the total power as the sum of the individual powers, and the individual powers as from the relationship of the power, the refractive index, and the two radii of curvature. Now if we want to correct for the chromatic aberration, we have to essentially bring the blue and the white light at focus at one point. So we can set the powers as equal for the wavelengths from the red and blue lines, F and C, and using the dispersion factor from the prism case, we can solve these system of equations. That will give us the individual power of the two elements required based on the dispersion powers of the two materials to be able to construct this kind of an optical system. So again, don't worry too much about the math over here. You can work that out by yourself. But what we should take home from this is the physics behind how we correct this kind of aberration. What we want to do is, instead of a simple lens, construct an optical element that allows the blue light to refract a little less and the red light to refract a little more, so that both of these 2 points come together. Both of the lights are focused at one point. And that's how we can cancel out the chromatic aberration. Okay, so this slide gives you a summary of different aberrations that you can find in different optical systems, like spherical aberration and what the character of that aberration is. So some cause image blurs and some cause off-axis blurs and so on, and what you can use to correct these problems. So you can look up each of these like space doublets, and in the case of chromatic aberration that we discussed, we use contact doublets, the crown and the flint. Alright. So let's try to wrap up what we learned so far. If we are to analyze an optical system, design an optical system, or construct an optical system, what we should be concerned about are these different factors. The ability of the optical system to form a bright image so that it gathers as much amount of light information possible, whether it causes any magnification or demagnification, as in the case of magnifying glasses, microscopes, or telescopes, what the resolving power of such systems are, and what other considerations would be the overall physical size, weight, cost, etc. Now let's look at a specific example of constructing an optical system, and let's take up the case of the astronomical telescope. So for the astronomical telescope, we have light coming from distant stars. Since this light is coming from very, very far away, it's again a bundle of parallel rays. They need not be traveling parallel to the optical axis, so let us consider that they're traveling at an angle. What we first want to do, and this is how we should analyze optical systems, is first we want to take all this light information and bring them to a point the size of which is manageable. Right now, let's assume that the diameter of this ray bundle is pretty big. So what we do is we take a big lens called the objective and gather all of these light bundles and bring them to a focus at a point on the optical axis. Now the first part of the problem is solved. We have been able to gather all the light information at one point. But now we have to look at this point, and right now it's too small to look at. So we will allow the light to divert just a little bit and then place a small lens in its path. What this lens will do is create again parallel rays from this divergent beam, but now the parallel rays have a diameter which is much smaller than the input diameter, and we can look at the exiting rays. So the second lens is called the eyepiece, because this is the final lens which guides the light towards our eyes, and the first one is called the objective. It's the one that focuses light rays onto a point on the optical axis. So we can define the angular magnification as the tangent of the input, as the ratio of the tangents of the input and the exit angles. And if you do the math, it gives you the ratio of the objective focal length and the eyepiece focal length. Again, this is important because if you are looking for a certain magnification of your optical system, you can choose two lenses for the objective and the eyepiece which have focal lengths related by the ratio which is equal to the magnification that you were looking for. That's why you have to keep this kind of math in mind, but overall it's I would suggest that what is more important is an understanding of what the physics is going on. Okay, so the angular magnification of the telescope can also be expressed by the diameter of by the ratio of the diameter of the entrance pupil to the diameter of the exit pupil. This is again comes from simple geometry, and you can work that out. Lastly, we come to the angular resolution of telescope. The lateral resolution is given by y prime, and the angular resolution is defined by y prime over f naught. So this is the y prime is the height of the point of focus from the optical axis, and if you look at the tangent, if this is of the tangent of the triangle which is made by the tip of the image to the to where the ray came from the lens, you can write this relationship. And the angular resolution gives us an idea of a very important criteria in case of optical systems like objectives, microscopes, and so on. That is the Rayleigh resolution. This tells you what is the smallest possible size that an optical system like a microscope can resolve. So if you're looking at very small objects, there is a limit to which you can essentially resolve those images, beyond which smaller images will not be properly resolved using your optical systems. And that criterion is called the Rayleigh resolution, and that is given by 0.61, which is a constant, and that comes from the characteristic of the optical system times the wavelength of light that we are using to look at the object, divided by half of the diameter, or the half of the diameter of the ray bundle. Alright, so again, let's keep in mind that when we are analyzing such situations, it's very useful to write the system matrix. In the case of the telescope, it would be you're looking from the output. So first you come to the thin lens condition, write this matrix for that. Then you do the propagation from the eyepiece to the objective, and lastly for the system matrix for the objective thin lens. So one more important thing to keep in mind, and you can work that out. So this is pretty easy. Just write the equations for the thin lens refraction. So you can see it's written over here, 1, 0, and that this term is essentially the power written as the inverse of the focal length of the eyepiece. The same is written for the objective, and d is the distance between the eyepiece and the objective. One important thing to note is d here is actually sum of f naught and fe, that is the focal length of the objective and the focal length of the eyepiece. So you can do the matrix multiplication, write these terms, and also keep in mind that D equals F0 plus Fe. Therefore, if you break down all kinds of optical systems, which is one of the most important points that I'm trying to emphasize in this lecture, whatever the optical system, whatever the complexity, if you remember the matrix formulations and the forms of the free space propagation matrix, or the translation to uniform medium matrix, and the refraction at spherical interface matrix, you should be able to break down any complex system into a set of matrices, multiply them, and you can relate the output matrix to the system matrix and the input matrix. That's the most important thing to take out from this lecture. Okay, so this is the last slide, and it shows us two different structures of telescopes. One is the Galilean telescope, and that works by using an objective lens and an eyepiece lens. But what this does is, if you have a huge bundle of rays coming in parallel to the optical axis, you first start focusing this down using an objective. But before it comes to focus, you place a concave lens. And if you remember, concave lens bends rays outward. So in this case, it's a converging beams. So if you have parallel beams coming into a concave lens, the parallel rays become divergent. So converging rays become parallel. So that is what is shown over here. And lastly, the Newtonian telescope is actually something we have already discussed. It's like the satellite dish or the radio antenna. It uses a paraboloid mirror to bring parallel rays to a focus at an image plane. Okay, so that brings us to the end of the geometrical optics lecture. I would suggest that you go through the sample problems, work them out by yourself, and see if you have any doubts or any questions. Feel free to get back to me, and I'll try my best to solve your problems. Thank you.